right, we have this big transfer orbit problem, number 5 on the homework, and we are going to step through it. And why am I thinking about chocolate chip cookies? Okay, first one, A, we're asked to find the period in seconds of a geosynchronous orbit. Well, basically that means that it takes the definition of a geosynchronous orbit is that it takes 1 day to orbit Earth, so basically we're finding out how many seconds in a day. 1 day is equal to 86,400 seconds. I know that because I counted them once. It took all, yeah. Okay, B, what is the radius of the orbit? It has to be done in green. It's big. How are we going to find this? We need some relationship between period and radius of an orbit, which is the Kepler's law thing, and I don't remember what it is, so I'm going to derive it. I say that this thing's going in a circular path, and the net force on it, on this satellite, is G, mass of Earth, mass of satellite, over radius of orbit squared, and that is equal to mass of satellite times its acceleration, which is v squared over r, but v is 2 pi r over t squared over r, and so that ends up being mass of satellite times 4 pi squared r over t squared. Mass of satellite cancels, goes bye-bye, and we're looking for r. Those are the same r because it's the radius of the orbit. And so we have to solve for r. Looks like r cubed is equal to a bunch of stuff. GME over 4 pi squared t squared. That's not right. That's not right. Okay, let's do some algebra. 4 pi squared is on the bottom, t squared is on top. That's not right either. Okay, we're already in trouble. Why does this look funny? Okay, the t squared is not there, so okay, you're gonna watch me fumble. I have to actually write this out and not do it in my head. G M E over r cubed is equal to 4 pi squared r over t squared. That's an r squared down here. It's going to become r cubed. So this t, what am I looking for? I'm looking for r. So this becomes G M E t squared equals 4 pi squared r cubed. It is that. It just didn't look right. So r cubed, and this t squared comes up top. So it is r cubed. This is really good. We're on part B, and I'm already getting screwed up. Is G mass of Earth t squared over 4 pi squared. Okay. And so now we got to put numbers in. R is cube root of 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The old man puts units in. Times mass of Earth, 5.98 times 10 to the 24 kilograms. Times period squared, 86,400 seconds squared. Divided by 4 times pi squared, and the whole thing is going to be cube rooted. And so now I will pause to punch the buttons. Okay, we got a number of 4.23 times 10 to the 7 meters. Should we even make sure that we end up with meters? I'm gonna. I don't know why I'm nervous about that. This is kilogram times meter per second squared for the Newton. So I've got a kilogram, one of those cancels. This kilogram cancels with that. I've got meters cubed. This meter times these meters squared is a meters cubed. And I've got a per second squared to go to the second squared. I end up with meters because I've got cube root of meters cubed. So that's got to be the right answer. Whew. Wow. That's B. Moving on. So that's the radius of the geosynchronous orbit. Remember, that's not the height above the ground. That is the radius of the orbit. And what do they want next? Okay. So now we're going to get something into that orbit by putting it first into a LEO and then a Hohmann transfer orbit into GEO. Part C is calculate the speed of the shuttle while in the circular low Earth orbit. So part C, I'm going to derive the formula. Do I have to derive it? this one, circular orbit, the speed of something in circular orbit is g mass of Earth over radius of orbit. That's, of course, for something orbiting Earth. And I'm not going to drive it because I'm lazy. And, okay, so this is going to be square root of 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times mass of Earth, 5.98 times 10 to the 24 kilograms, divided by radius of the orbit, which is the Earth radius, because they give us a distance above the Earth's surface, 6.37 times 10 to the 6 meter Earth radius, plus 400,000 meters, 4 times 10 to the 5 meters. Square root the whole friggin' thing, and that gives me a V of, and I will pause and do the calculation. And my friend on the calculator says that this speed of this thing is 7680 meters per second. I'll round it to. Okay. That's the speed in low Earth orbit. And so now we're going to put this thing into a transfer orbit, which goes from low Earth orbit to geosynchronous orbit, goes from LEO to GEO. And this is where the problem starts to get interesting. We're not just doing the circular orbit thing, we're going to do some elliptical orbit stuff. All right. So there is no, calculate the speed of the satellite in the transfer orbit at perigee. All right. So this is where we have to start doing some new stuff with this elliptical orbit. So we're going to do the physics. So I'm just going to label this transfer orbit. And what do I want? I don't want to just do the problem because I want you to figure out as much as you can. If you're watching this video, it's because you got stuck on this somewhere. And so let's see. I need to sort out what I know about this transfer orbit. I do know, for instance, the size of the transfer orbit. So one of the things that I'm going to have to do here is, so I'm just going to draw this transfer orbit. With the Earth, just for reference, over here somewhere. So this line is the actual orbital path. And it's an elliptical orbit, and I'm going to be interested in taking an energy approach here. Because I know that the energy of this satellite in the transfer orbit stays constant, but it's exchanging potential for kinetic energy and vice versa. And so I'm going to be interested in a couple of different things that I can use to analyze this elliptical orbit. One of them, as I say, is energy. I know that if I can find the total energy that the satellite has to have when it's in its orbit, then I might be able to figure out speeds and stuff, or heights from speeds, based on conservation of energy, knowing that the energy is made up of potential and kinetic. Another thing that I can use, another tool that I have for this, by the way, and this goes back to stuff we did a couple chapters ago, is angular momentum. The satellite, when it orbits around this central body, there is a conservation, I'm just going to write this down, of angular momentum. And because the gravitational force, which is the only force acting on the satellite, does not create a torque. And so there's no external torque on the satellite, so its angular momentum about the Earth, in this case, stays constant. We may or may not find use to use that, but it's another useful tool for analyzing elliptical orbits. So the first thing I'm going to do is take the energy approach. So I encourage you, if you haven't yet, to see if you can figure out what the energy of the satellite is in this transfer orbit. And so I'm going to do that now. And I'm going to do that. I'm going to just keep that out. The conservation of angular momentum, keep that as a thought in the back of our heads in case we end up needing to use that. But I'm going to start with the energy approach, as I said, and I'm going to first of all find the total energy of the satellite in this orbit. And in an elliptical orbit, that is g times mass of the Earth times mass of the satellite, all divided by by 2a, where a is the semi-major axis. Okay, remember, a is the semi-major axis, so 2a, just going to make a note here, is the whole major axis, because a is half of the major axis, so 2a is the whole thing. The major axis is the distance across the elliptical orbit in that direction. And oh, no, I'm not. Oh, come on, board. Oh boy, board's getting funky. Okay, I'm going to draw this in red for some reason. Because green doesn't work anymore. Anyway, this is the major axis, 2A. And do I know how far that is? Well, I do, because from the Earth to this closest point, which we call apogee, that is the radius of the Leo orbit, low Earth orbit. And the distance from the center of Earth to the farthest point over here is, if you look at your diagram, this is the radius of the geo orbit. And so those two added together, 2A is equal to R Leo plus R Geo. And we know both of those values. So 2A is equal to, the R Leo is back up here. It is the radius of Earth plus the height of the satellite above the Earth's surface. And if you actually do that math, you get 6.77, there's a decimal here, times 10 to the 6 meters. And then radius of geo is what we got back in part B, 4.23 times 10 to the 7. 4.23 times 10 to the 7 meters. So 2A, the major axis, is the sum of those, which is 4.91 times 10 to the 7 meters, I hope. Yeah, and so that's useful. And so what are we looking for? The speed of the satellite in the transfer orbit at perigee. All right, so I almost can come up with the total energy of this thing. They never give me the mass of the satellite. At least I don't think they do. And I shouldn't care because, unless they ask me about an increase in energy. No, they just, so I shouldn't care because the speed of a satellite in its orbit is independent of its mass, which is why the astronaut can orbit alongside the space shuttle or whatever, even though they have different mass. So I'm not going to ever actually calculate this amount of energy that it has because I don't know the mass of the satellite. So I'm going to have to trust in the idea that this divides out in subsequent calculations. Now I'm looking for the speed of the satellite at this point, which I'm going to call point P because that stands for perigee. And so that's point P, and I'm looking for the speed there. So now what I'm going to do is I'm going to take this energy approach and say that at point P, this is the satellite, and actually it's the satellite Earth satellite system at P, when the satellite's at P, because these energy expressions are for the whole system. And I'm going to say that the energy at that point is equal to kinetic plus potential. Okay, and so I'm going to sub in equations for all these different kinds of energy for this satellite in a circular orbit, in an elliptical orbit. Okay, the E, total energy, is negative G, mass of Earth, mass of satellite, over 2A, and we found 2A, we have that value up above, equals kinetic, which is 1/2 mass of satellite V of satellite squared, remembering that the Earth isn't moving, because we're looking at it from that frame of reference, and its infinite mass, plus potential energy, the two-particle system, which is just negative G, mass of Earth, mass of satellite, over R squared, where this is the distance between them at this particular position. This is a variable during the elliptical orbit, but it has a value, which is the R Leo at this, so it's not a variable at this one particular time. At this particular time, it's the radius of the low Earth orbit. Okay, so I believe that we know, okay, we don't know mass of satellite, but look at this, boom, 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 it cancels out. And I think we now know everything else that we need to find Vs, the speed of the satellite. So let's be a little careful here with the algebra. I'm going to add this term to the other side and multiply through by 2. I'm going to get Vs squared equals this term added to the side. Oh, boo, 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 boo. I made a goof. I'm glad you caught it for me. That's not r squared, you moron. This is potential energy. It's just plain old r. Ha ha ha. Good joke. So, I'm going to add that term to the other side. It's going to become positive. G mass of Earth over r Leo. So that got added over here. Minus this guy. Minus G M E over 2a. And I have to multiply, this is 1/2. Okay, so now I can multiply through by 2. And I'll write one more line of algebra before I plug numbers in. So I have Vs is going to be square root of, I can get all kinds of fancy, in fact, I've got a GME I can fancy factor out. So I'll have 2, because this 2 gets multiplied over to the other side, 2 GME. And now I have 1 over r Leo minus 1 over 2a. And I'm going to square root that. Okay, now I can put numbers in, and then I can do a calculation. Vs equals, you're going to watch me sub in the numbers. 6.67 times 10 to the minus 11 meters squared per kilogram squared. Times mass of Earth, which is 5.98 times 10 to the 24 kilograms, times 1 over r Leo, which I remember that number, 6.77 times 10 to the 6 meters, minus 1 over 2a, that's the major axis, which I just got up here, 4.91 times 10 to the 7. 1 over 4.91 times 10 to the 7 meters. The whole thing is going to be square rooted. All right, now I'm going to do some math. Okay, I got a speed of the satellite of 1.01 times 10 to the 4 meters per second, which makes me happy because it is faster than the speed in the circular low Earth orbit, and it's not the square root of 2 times that. It's not that big, I don't think, which would make it greater than the escape speed. So this is actually a plausible value. Okay, that is part. Let's go. That is part D. E. Oh, this is easy. What is the change in speed required to change it from Leo to the transfer orbit of perigee? That's just how much did I speed it up. That's a delta V. Is V transfer minus V Leo, which is this number, 1.01 times 10 to the 4 meter per second, minus the speed in Leo, which is, where is that back here? 7680. Minus 7, I'm going to call it 0.68 times 10 to the 4 meter per second, so I can do the subtraction more easily. And my delta V equals, I'm going to have to do this. 1.01, whoops, 1.01 minus 0.768. This isn't working. 1.01 minus 0.768 is, okay, 2420 meter per second. That's how much you have to speed it up with a relatively abrupt kick in the butt. Okay. So F says, what is the speed of the satellite in the transfer orbit at apogee? So basically what we're saying now is here's Earth, here's the transfer orbit, excuse me. The satellite was given a boost in speed of 2420 meter per second, so it's going faster now than it was in Leo. It now travels in this transfer orbit out to the furthest point, at which time it's going slower, because it's farther away from Earth, and they're asking us what is the speed here. This is a time where there are two strategies we can take to calculate. So I'm going to call this P for perigee and A for apogee. And it has, so this is V, P I'll call this, and this is V, A. And there are two ways you can find the speed at this point. A really hard way and a really easy way, or relatively hard. And I will tell you that the relatively hard way is conservation of energy. And it's just clunky because the terms are complicated, relatively complicated. The far easier way is to use conservation of angular momentum, just because the equation's a lot simpler to look at. And so I encourage you to try the energy approach because it works, but the conservation of angular momentum approach is a whole lot simpler. Mostly because we've picked these 2 points where the velocity vector is at a right angle to the r vector, and so when you do your angular momentum, well, the stupid green pen doesn't work. So when you do your angular momentum, here's your r vector. If they're at a right angle to each other, the angular momentum, the cross product stuff doesn't really make any difference. It becomes much easier. Sine of phi is 1 or something like that. Okay, so let's do it. LP equals LA. And so, again, the angular momentum of this particle, we're calling this a particle, is r cross p, or the magnitude is r mv sine phi. But phi is the angle between r and v, and it's 90 degrees, and so that gets arrowed 1. Okay, let's be clear about this. R is RP, and VP, M doesn't change, equals RA MVA sine phi. And again, out here, we have the R at this point is again at a right angle to the V, and so sine phi becomes arrow 1. The mass drops out, not surprisingly, and so VA simply is the ratio of the distances, RP over RA times VP, and this, I have these numbers somewhere, the distance at perihelion was, I gotta look it up, 6.77 times 10 to the 7, no, times 10 to the 6 meters. And the distance at aphelion, which is in the geosynchronous orbit, is this number we got way back a long time ago, 4.23 times 10 to the 7. Sorry if that gave you a headache watching that scroll so fast. 4.23 times 10 to the 7 meters is a 10. And it's that ratio times the speed at perihelion, which we just got is 1.01 times 10 to the 4. That's a point times 10 to the 4 meters per second. Okay, so let me pause and do this calculation. Okay, and I got 1.62 as a point there, 62 times 10 to the 3 meters per second, or in English, 1,620 meters per second. Whereas here it was going 10,000 meters per second, so it has slowed down a lot to a pathetic, 3,500 miles an hour or something like that. Okay, so that's the speed that it has at apogee. So now what we have to do, if we don't do anything, if we just let this thing coast, it's going to continue to follow this this elliptical orbit, this transfer orbit, and it's going to go from its position out here at the same distance away from Earth as Geo. But if we just leave it, it's just going to follow this transfer orbit forever. So at point A, we need to change its speed to the speed it needs to continue in the geosynchronous orbit. So we need to find out what that speed is, unless we already have. I don't know if we have already done that or not. Speed in geo, I don't think so. Transfer orbit, this is speed in Leo. Yeah, we haven't. So we got to find that. We have everything we need to do it. It's a circular orbit. Ooh, so I'm going to find the speed in geo. I think this is part G for geo. And V geo, it's a circular orbit, so I can just use square root of G times mass of Earth over radius of orbit, which is the radius of the geo orbit. And that is square root of 6.67 times 10 to the minus 11, all that fun stuff, times mass of Earth, 5.98, times 10 to the 24 kilograms, all divided by radius at geo, which is not that, it is 4.23 times 10 to the 7 meters. Yeah, that's right. Okay, 4.23 times 10 to the 7 meters square rooted. So I'm going to do that calculation. And I get 3,000 3,071, basically 3,070 meters per second. So we have to give it a pretty good kick in the butt. It's going 1620. We have to do another rocket burn essentially to increase the speed up to 3,070, and then it will happily circle Earth in this geosynchronous orbit and perform the important functions of beaming down reruns of 1960s television shows, so you can watch them on the TV when at work or something like that. I think we're done. Thank you very much.